So welcome everyone. Here we go for the benefit of all students. Here is a small revision of the exam coverage for grade 9 advanced physics term 1. We'll try to cover all the points, and here we go with the first. So in the first point, they are asking us to define the term scientific method and list the common steps. So we can see this point, or we can discuss it from the book where they start, or that's what you call by the scientific method, where it combines lots of steps starting by the state of the problem. Then we gather information, we form a hypothesis as a third step, we test it, we analyze the data, and we draw a conclusion. So these are the main steps of the scientific method. Most importantly here, they stress on the hypothesis. Here in question 2, define what is hypothesis. So it's a possible explanation for a problem using what you know or you maybe have observed. So it's a scientific hypothesis can be tested through what? Through experimentation or and observation. Here I created a small scenario for a problem that we all faced, I assume 2 years or 3 years ago, where we faced the problem of COVID-19, the coronavirus. So I will go through these steps of the scientific method that require to solve the problem of the COVID-19, which was a global problem. Okay, so first of all, we state the problem. Okay, so in December 2019, the health authorities in many countries, okay, notice the unusual case with some symptoms. So something problem, okay, or something bad is going on, but they don't know what's going on yet. So scientists and health experts, means doctors, start asking questions. So that's the statement of the problem. What is causing this outbreak of this illness? So they know that something bad is going on. So it's an illness, but we don't know yet. Okay, so we don't know if it's COVID or something else. It's an illness till now. Then they start to gather information. They start doing tests for those affected in different countries. Remember, they start doing PCR for everyone. So they start, doctors or researchers, they test. Okay, so we are gathering information, okay, from different places. Then they form a hypothesis. So researchers hypothesize, they think that the outbreak could be caused by something that we don't know yet. It's a new virus that affects the respiratory system, okay, of the people. So it's a virus affecting that's what they think. It's a hypothesis. Then they go to try this hypothesis by isolating. Remember, they start to isolate or quarantine, if you remember the word. They isolate the people affected by this virus and to test. They are testing this hypothesis, okay, to see if the virus continues spreading out or no. Then they analyze the data that they already gathered in the previous steps, and they compare this new virus that we don't know to already known viruses. Like, you know, there are multiple viruses in the air, so they start to compare the symptoms of this new virus to the old one or the known viruses. Okay, and then we draw a conclusion. So based on all the steps that we go through previously, then they have a conclusion. There is something new is going on. Okay, there is a new virus. They call it coronavirus. Okay, that caused this problem. Okay, a disease called by COVID-19. So these are the steps of a scientific method, and scientific method could be applied to millions of examples, not only one. I choose this example assuming that all of us gone through these problems. Okay, then we continue. In the third question, they ask, if you remember, they ask about models. So these are two models I picked from students. So a model of an atom, as you see, it's a model containing electron, proton, and nucleus. And here is another model. It's about the solar system. I hope my voice is still going on. And this is a model of the solar system. Okay, so what's the point or what's the purpose of a solar system, of a model that make things easier to us to understand. Okay, that's why we make models. Okay, so the models make things, simplify things, or make it easier for us to observe or to experiment. So we continue with the models. Here are 3 different models of atoms, starting with 1904. It's a very old model of an atom. Then this model have been developed by Rutherford in 1911, and then this model also have been developed by a group of scientists to reach this model that we're still using, the electron cloud model. Okay, so you see, models are developing year by year. Okay, they are not fixed. Okay, this is another model of molecule. Okay, so models are not fixed. Models can be developed by the time, by years, by the technological advancement. So a model is a representation of an idea, event, structure, or object that helps people better understand the event or the phenomena or even nature. Okay, so if you go back in question, I remember maybe in question 5 they ask how many theories to explain the law of. Okay, here in question 5 they ask us to differentiate between law and theory. So as you see here, we have 4 different theories. So first theory about the Greek philosophers who trying to explain what's gravity. Okay, so they assume that objects want to go to their mother earth, that's why they fall down. Okay, that was the thinking or the philosophy at the time, that objects fall down because they want to go to their mother. Okay, that was a very old idea or theory, let's say. Then Galileo came and told us or upgrade this theory to claim that that 2 objects, it's still about the gravity, the 2 objects fall down, okay, on the same and reach the ground on the same time. That was shocking at the time because they assumed that bigger objects or heavier objects reach the ground faster, which Galileo proved that 2 objects falling down reach the ground at the same time. So this is another theory of gravity. Then we moved on to Newton's, who proved if you remember the Newton's, what do you know now, but by Newton's second law, F equal ma, talking about acceleration as well, or free fall. So these all ideas have been described by Newton's laws. Okay, then lastly, or the last theory we reach is by Einstein, who described gravity in function of time and space. It's a complicated theory, but as you see here, we have multiple theories trying to explain one law. Okay, one law, which is the law of gravity. Okay, so again, multiple theories for one law. We continue with the second point, now talking about recognized physical quantities like time, mass, temperature. Okay, so in the book again, you see different quantities and their units, and most importantly their symbol. So length, what's the unit of length? Is meter. Unit of mass, kilogram, of course, kg. Unit of time, seconds. Temperature, Kelvin. Okay, so this is an abbreviation or a summary of the main units used in physics: length, mass, time, temperature. So we have to know these units. It's essential, it's basic, and that's what we call by international system, or SI. System international units. So why it's called international? Because it's not applied in one country or group of countries. It's international. So even if you travel to anywhere in the world, you told them meter, so they understand what's meter. If you told them about the kilogram, they understand what's kilogram. Okay, so these units are applied everywhere in the globe. So that's why it's called international system. So moving on, this will lead us to the third point, to talk about dimensional analysis. Okay, so the relationship between the units itself. So as you already know, that 1 kilogram is equal to 1,000 gram. Okay, so every 1 kilogram, so here I'm writing for you, 1 kilogram is 1,000 gram. So here they are asking to convert 1.34 kilogram. So what to do? We have to multiply by 1000. So that's why we convert from kilogram to gram. Okay, so 1.34 equal to 1340 grams. Okay, here is another way. What if we have two types of units, kilometer, which is about the length, distance, and hour, which is about the time. So what if we combine these two units, kilometer and hour? So here they are asking us to convert from kilometer per hour to meter per second. So we first have to convert kilometer to meter by multiplying by 1000, and then we convert hour to seconds, okay, which is 60 by 60, which is around 3600 seconds. So instead of going through all this long way, I'm writing for you here a new way or easy way to convert from kilometer per hour to meter per second by dividing by 3.6. So by simple division by 3.6, we go from kilometer per hour to meter per second. Okay, that's the easiest way or the shortcut. Or what if we want to go from meter per second to kilometer per hour? We have to multiply by 3.6 then. Okay, here we go with the number 4, point number 4, determine the source of error and distinguish between precision and accuracy. So the famous example about the arrows to differentiate between accuracy and precision. So in the first picture, because the arrows hit the yellow target and all of them hit the same point, so they are, in this example, it's a good example of accurate and precision. Okay, so that's what we mean by accurate and precise. What if the arrows are away from the yellow, but all of them come to the same point? They are still precise. You see how precise they are? All of them hit the same point, all the 3 arrows. But unfortunately, they didn't hit the yellow. So it's not accurate. Okay, only accurate if it hits the yellow. If the answer is correct, okay, then it will be accurate. In this case, it's precise, yes, but not accurate. In the third case, all arrows are separated and they are away from the yellow. They are separated. So it's neither accurate nor precise. It's inaccurate and imprecise. So in short, how to define accuracy, how to go with accuracy. So if they ask us or how to make sure that an instrument is accurate, so a common method to do that is to check if the instrument reads 0. So for example, if I want to measure my weight, the balance or the instrument have to read 0 at the beginning, otherwise it will give me a wrong answer. So that's a way to measure or to check accuracy. Okay, so again, to describe accuracy is described how well the result of measure agree with the real value. Okay, and how to make sure or how to check this out by or when checking the 0 in the instrument before using it. That's for accuracy. Moving on to techniques of good measurement under the same point as well. Here we go with parallax. So here we have same instrument, same value, but look what's wrong here. Here we see in the first correct reading, we see it straightforward, okay? So it's just in front of our eyes. But what's wrong in the second one? We see it from above. So when we see the instrument or we're trying to read from different angle, so this will lead to an error. This will lead to a mistake. So what do you call it, by different angles. So to avoid this, we have to go with correct reading by looking straight to the instrument, okay, without any angle. Any little deviation or an angle will lead us to a reading mistake in the instrument, and that's what we call by a parallax. With the point number 5, measure the base quantities and some derived quantities using suitable measurement tools and record those measurements taking into account significant figures and scientific notation. Very important. The significant figures and the scientific notation. Here they gave us in the book a small example by adding two numbers, first with the 3 significant figures and the second with 2 significant figures. So how to know the answer? Okay, the answer, how many significant figures, how do I know how many significant figures have to contain? Okay, how do I know? So we have to look, or we go with the least precise measurement. So this means that the answer have to contain only 1 digit after the decimal, like here. Okay, so with the least, this is the least, 2.4. Okay, because it contains 1 digit after the decimal. This is not the least, 3.86, because it contains 2 digits after the decimal. So I go with this. So this means I take only 1 digit after the decimal. So the answer have to resemble 2.4, which is 6.3. Only 1 digit after the decimal. In the second example about the division, here we have also 2 numbers. We are dividing 409.2, which means 4 significant figures, and divided by 11.4, which is 3 significant figures. Here I think it's easier because we go with the least significant figure, which is 11.4. So which contain 3 significant figures in this case. So at the answer have to contain as well 3 significant figures. That's in case of division and multiplication. Here is a small example asking us to solve the following problem using the correct number of significant figures. So I will start with this one, 4.75 minus 0.4168. Okay, so first of all we have to write it correctly. Okay, we have to put the decimal after the point under the point. Then, because here there is gaps, because of the gaps I add 0. Okay, I put zeros here. But can I subtract 8 from 0? No. So I have to borrow from 5. I have to take 1 from 5. So 5 turned to 4. If you remember, you learned this in math in previous years. 5 is turned to 4 in that way. And then the 0 here converted to 9. And 10 first, and then because of 10, giving 1 to this 0, so this one turned to 10, and the 0 here turned to 9. So now it's 10 minus 8, which is 2, 9 minus 6, 3, 4 minus 1, 3, 7 minus 4, 3, 4 minus 0, 3. But how do I know the correct answer? Okay, here we have to draw a line with from here. We have to draw a line, if you remember in the previous slide, with the least decimal point. For example, here 4.75 have 2 digits after the decimal. 0.4168 have 4 numbers after the decimal, which is, so I have to draw the line here beside 5, and that's how I draw it, beside 5. So it means that I have to stop here, and the answer is 4.33. I don't count the last 2, so I have to stop at 4.33. So again I draw the line beside the 5. Another example, 10.8 minus 8 points. Again we have to write it again, decimal under decimal, put the gaps zeros, and then I draw the line. Okay, so I put the gap 0 here, and then convert 0 to 10. 10 minus 4 is 6. Now 9 minus 6 is 3. 7 minus 2 is 5. The decimal 10 minus 8 is 2. So, and then I draw the line beside 8, because this is the least decimal number. Okay, so I have to stop at here at this point, 2.5, without taking into account the 36. Now about the significant figures. All numbers are significant. Okay, from 1 to 9, all of them are significant. So all of them, but where is the problem with the zeros? Sometimes zeros are significant, sometimes it's not, and that's what's making the problem. So if 0 is on the left, it's not counted. So in this case, it's not significant. And that's how we write this, the scientific notation. We move the comma 3 steps, 1, 2, 3. So that's why we write 10 minus 3, because I'm moving the comma to the right. What if the 0 is in the middle between 2 digits? So it's counted, it's significant. Okay, so if 103, the 0 here in the middle is significant. Okay, it's significant. Here in the third case, to the right of non-zero digits, for example here. So if we have a decimal number, okay, 1520.0. So in this case, it's decimal. Sorry, it's significant. Okay, because we have a decimal number. Okay, it's significant. What if we don't have a point or decimal? So the 0 in this case is not significant. I hope this is clear for all of us. Now moving on to point number 6. Analyze the curve position versus time graph, velocity versus time graphs for an object moving along a straight line in a uniform or non-uniform motion with constant or variable acceleration. Okay. And equation of motion solver. Okay, yes. So first of all, to start solving such questions, first step is to calculate the slope. Okay, so all of us know the slope is the delta y over delta x. Is the change in the y-axis over the change on the x-axis. So in this case, it's a position time graph. We have the table. We put the points on the axis, on the coordinate system, and we draw the line. And that's what we get. So after drawing the line, I look for 2 points. Any 2 points on the graph, but for me I choose now I choose 0 and look here, I choose 0 and the maximum point here. I prefer using 0 because it's easier for the calculus. So it's y2 or y final minus y initial. So y final, which is 30, minus 0, that's what we got here, 30 minus 0, over divided by x final, which is 6, minus 0, which is so 30 now divided by 6, which is 5. So that's for linear. What if it's non-linear relationship? For example, here the quadratic relationship. Okay, every time you see a quadratic relationship, so of course it contains a square. So here is the equation: y equal ax squared plus bx plus c. So this equation describes this kind of curves, which is the quadratic, or we describe it as quadratic relationship. What if it's you see here it's going down? Okay, it's falling down. So that's what we call by inverse relationship. Okay, if the curve is falling down, so that's an inverse relationship, and the equation in this case is y equal ax. Here is a small question to solve. I choose it for you. So what is the slope of this graph? So they gave us a graph and they ask us for the slope. Same thing, to calculate the slope, we define the 2 points first, and then y2 minus y1 over x2 minus x1. So in this case 1 minus 0 over 4 minus 0, which is 0.25. So y2, which is 1, okay, minus y1, which is 0, I choose 0, divided by x2, which is 4, minus 0, so it's 1 over 4, which is 0.25 meter per second square. Okay, so here we are with point number 7. Explain the instantaneous velocity. So how to define this? So it's the speed or direction of an object at a particular instant. Okay, that's the most important part. It's a particular instant. That's why we call it instantaneous. Okay, so a good example of that is the speedometer in the car that gave us the speed at each second. Give us the speed of the car at each moment. So it's a good example of instantaneous acceleration. So for this point, I choose question number 29. So what is the average velocity of an object that moves from 6.5 centimeter to 3.7 centimeter relative to the origin? So this object is approaching the origin because it was far away, 6.5, and now it's becoming closer, getting closer to the origin, 3.7, with the time of 2.3 seconds. So first of all, to calculate the velocity, which is, as you know, deviation or the change of x over the change of time. So change on x, which is x final minus x initial. So final in this case, it's 3.7 over or minus 6.5, which is the initial, over the time which is 2.3. So the answer is 1.2 meter per second. We put minus because it's opposite to the positive direction, because it's coming closer to the origin. That's why, or that's the reason behind the minus. Most importantly, it's 1.2 meter per second. Moving on to point number 8, analyze a position time graph to describe the object motion. So here I choose, or we go with figure 19 as described here. So we have two players. Okay, so we choose also to define the slope of a position time graph. The slope of a position time graph is the velocity, which is meter per second. Okay, so usually we choose 2 points, here in the red and here in the black. Okay, here in the example in the book, they choose 2 different points, which is y final minus y initial over x2 over x final minus x initial. So in this case, it's 6 minus 2 over 3 minus 1. And the answer is 2 meter per second. So the red jogger is too fast. Okay, 2 meter per second. What about the other player? Also we pick 2 points. You can pick whatever you like on the line. So x final minus x initial over t final minus t initial. So x final, x final, which is in this case the position, which is the 3, minus the second point, which is 2. Okay, over t final, which is 3 seconds over 2 seconds. And the answer is 1 meter per second. Okay, so it's a position time graph where the position or the distance or the displacement in this case is on the y-axis. Here is another example from point number 9. Conduct an investigation to show different kinds of motion using a motion diagram and particle models. So here is a good example. Using the particle model motion diagram in figure 16, this one, of a baby crawling across a kitchen floor, plot a position time graph to represent the baby's motion. Okay, the time interval between the successive dots on the diagram is 1 second. So this means that the baby has a constant speed because the gaps or the distance covered for each second is the same. From 0 to 20, 20 to 40. So you see the distance covered is consistent. The same gaps in each 2 consecutive points, same gaps. So we can deduce that the baby here has a constant speed. Okay, because for each time, for each gap, for the same time interval, the baby crossing the same distance, which is 20 meters. Here is another example. Use the hockey puck's position time graph to determine the time when the puck was 10 meters beyond the origin. So 10 meters. So which axis describing the distance or the meter is the y-axis here. They are talking about 10 meters. So it's the point between 0 and 20 here in the middle. Okay, which is 10 in this case. So I bring a line and I see where it hit the green line. And here it is the time for 10 meters, which is 0.5 seconds. Here, point number 10 and point number 12 share the same or share the common idea about describing the motion of velocity and acceleration vector. So here I pick for this figure number 4, where we have 4 position or 4 different scenarios of a car moving, where in the first case acceleration and velocity are parallel and going in the same direction. So in this case, the car is speeding up. What if the acceleration vector and velocity vector are opposite? So in this case, the car is slowing down. Okay, and here I write it for you. So in this case, in the 1 and the 3rd, speeding up. In the 2nd and the 4th, the car is slowing down. And you can deduce the same idea from the points. When the points start to diverge from each other, they go away from each other. So we can tell that the car is speeding up. If the dots or the position of the car start to converge or to come together, So we can tell that the car in this case is slowing down. Okay, so how to define acceleration in this case? Instantaneous acceleration from velocity timing graph is simply by dividing the velocity by the time. Okay, so delta V, which is V final minus V initial over T final minus T initial. A good example of that is this one. A bus is moving west at 25 meters per second. When the driver steps on the brake, means want to stop. The driver step on the brake and brings the bus to a stop. Stop means velocity is equal to 0 after 3 seconds. So what's the average acceleration in this case? So here initial speed, which is 25 meters per second, and the final speed is 0 because they told us that the bus stop. So of course the velocity in this case, or the speed, is 0. And the time for that scenario is 3 seconds. So question 1, what's the average acceleration? So of course, as we learned in the previous slide, it's the change of velocity over the time. So V final, which is 0 minus V initial, 25 over the time. So acceleration is negative. This means that the bus, of course the acceleration have to be negative because the bus is slowing down, want to stop. So in this case, acceleration is negative. We continue, the bus took twice as long. What the meaning took twice as long? Means that the time taken is multiplied by 2. So instead of 3 seconds, now we have 6 seconds. So 2 multiplied by 3, we have 6 seconds. So the new acceleration is, I call it A prime. It's V final minus V initial, never changed, still the same, 25, over the time, which is double this time, which is 6. Here I forgot to put the minus. It's negative 4.1 meters per second square. Okay, so the acceleration in this case is less. When time increase, okay, when the time increase, the acceleration will be less. We continue. I guess that we passed the 30 minutes, but no problem. Okay, here analyze a curve of position versus time graph and velocity timing graph for object moving along a straight line in uniform or non-uniform motion with a constant variable acceleration. Okay, so here the velocity timing graph from question 3, figure 9, to find the average acceleration of the train during the following intervals from 0 to 5 seconds. So this is 0. Where is 5 seconds? It's here. So I pick 2 points, this one and this one, of course, 0, and I calculate V final minus V initial over time, which is 2 meters per second square. So V final, which is here 10, minus 0 over x, here x, which is between 0 and 10, which is 5. Okay, minus 0, which is 5, or equal to 2 meters per second square. Going to the next one, I choose these 2 points in the black. So again, V final, which is 4 minus 10. So V final minus V initial over T final 20 minus T initial 15, which is 5. So the acceleration is negative because it's going down, it's negative. So minus 1.2 meters per second square. Question number or bullet number 14. Apply the equation of motion relating to the final position of an object to its initial position, velocity, uniform acceleration. Okay, we can choose any problem between 23 or 27. So I choose question number 24. So a race car travels on a straight racetrack with a forward velocity of 44 meters per second and slows at a constant rate of 22 meters per second over 11 seconds. So how far means, so first step is to write the given. First velocity, second velocity, time, and the distance, because they ask how far. Okay, so we have 2 velocities and we want to calculate the distance. So what to do here? Here we need to calculate the average velocity. So to do that, first of all, we have to recognize the equation. Okay, the average velocity in this case, which is V bar, is delta V over 2. So it's V final, which is, or V2, which is 22 minus 44 over 2. And the answer is minus 11 meter per second. So that's for the velocity. Now the time is 11 seconds. So just simply multiplication to calculate the distance, which is equal to velocity multiplied by time. If you remember, very old equation, still using till now. Distance equal velocity by time. Velocity or average velocity, which is minus 11, okay, multiplied by 11 seconds, which is equal to 121 meter. Okay, or minus 121 means the object or the car is moving in opposite direction to the positive axis. We are approaching the end of the video. Here we are with bullet number 15. Analyze the position time graph and velocity time graph and acceleration for an object under free fall. Here is an example of a free fall position time graph. So first of all, the ball, when you're throwing the ball will go up, stop here in the top, stop, and then change its direction, and then it falls down. Okay, so at the top, what's going on? The trajectory change its direction. So at the beginning it was increasing, at the top it's 0, and then it starts to decrease. Okay, so here is stop. What the meaning of stop? Means the velocity will become 0. So here is the same representation. So for the free fall, position time graph, velocity time graph. So at the beginning you throw the ball at very high speed. You throw it here at very high speed at the beginning, which is here, it was 20. When you lift the ball start to lose the velocity little by little. At the top, what happened? The ball hang out in the yes, the ball have when reaching the top have a 0 velocity. Okay, this means here the velocity have to be 0. So this square represent also this square. They are the same, but that's for position time graph, and this is describing the velocity time graph. And then start to decrease. Okay, after that the ball start to decrease or moving, okay, in the negative direction. An example on that from question 1, identify the variables in tabulated data and represent them in a suitable graph. So maybe here they will give us a table and we have to draw the graph, pinpoint the graph, XY axis most probably, or velocity time graph between variables to obtain the mathematical equation describing the relationship to determine the value of the dependent variable. Okay. Identify the relationship between the average change of a function between 2 points and the slope. Okay, here I choose question number 19 as they advise. So a car slows, they are telling us it's slowing down, huh? So acceleration of course will be negative from 22 meters per second to 3 meters per second at a constant rate of 2.1. Here they're supposed to write minus 2.1, but no problem because they already describe it as slowing down. How many seconds, so it means time, are required before the car is traveling at a forward velocity? So we have the initial velocity, we have the final velocity, and we have acceleration. And they ask us to find the time. So here is the given velocity, final velocity, initial, acceleration, and time. So we apply this equation, v final equal v initial plus at. But in this case, as I told you, acceleration is negative because it's slowing down. You have to be aware of that. So v final, which is 3, equal v initial 22 minus acceleration 2.1, yani minus 2.1 multiplied by the time. So by simple use of calculator or by arranging the equation, we get that the time is 9 seconds. So the car to slow down from 22 to 3 meters per second at this constant rate, it will take 9 seconds. Here question 2 and question 3 are similar because they are asking us to solve problems on combination of equation of motion. So for that I choose question number 35. The airplane in this figure starts from rest and accelerates east at a constant rate of 3 meters per second square for 30 seconds. So the time is 30 seconds and acceleration is given 3. So what's the plane displacement delta x? So this is delta x here. So because they told us start from rest, means that the initial velocity is 0. Acceleration is given 3, time required 30 seconds, and asking in question A for delta x, or the distance, delta x. Okay, so what equation to use here? Which is delta x equal VIT, which is initial velocity multiplied by time plus half AT square. As advised, or as I told you, that initial velocity is equal to 0 plus half A is given 3 multiplied by time, which is 30 square. So delta x equal 1.35 by 10 power of 3 meter. So it will take the airplane this distance before taking off. In question B, they ask how fast. So asking for velocity. Okay, so how fast means the V final, because we already know V initial is 0. So we use this equation. V final equal V initial plus AT. V initial equal to 0 plus A acceleration is 3 multiplied by 30 seconds, 30. So the final velocity is 90 meters per second. Okay, with the last question. Okay, so a construction worker accidentally dropped a brick. So this is question 41. It's about free fall, I guess. Yeah. Okay, free fall during or rising a falling motion. Okay, so drop. Again, what the meaning of where the drop means without any initial velocity, no initial velocity. So free fall, it's an example of free fall where the acceleration is, don't forget, it's minus 9.8. So in case of a drop means the initial velocity equal to 0. So what is V final? So V final will be equal, same equation as we used in previous slide, equal VI plus AT. Initial velocity again is 0, acceleration is minus 9.8 multiplied by the time. So V final, it's negative because it's falling down, going in the negative direction. Okay, so it's 39 meters per second. In question B, how far means delta x. Okay, so we use it in the previous slide again. So VI equals 0 because it's dropped down plus half A minus 9.8 multiplied by the time. So the answer is minus 70.8. Yes, minus 78 meter. I think it's already 40 minutes. Thank you. That's it for now. I think it's over. I hope you all do well. This is for the benefit of all grade 9 student advanced. Thank you so much.